Okay, so this is the so let me take an explicit example of a QED theory. So this is the uh, nth term, and you sum over n from 0 to infinity, and you integrate over this. So you might call it a covariant expression for the Swinger-Dyson equation, right? You have the Schrodinger equation, you integrate it, and the integral equation that you got, and if you do it n times, that is in quantum mechanics, you get the Swinger-Dyson equation, and you write the corresponding covariant expression for this perturbation theory of quantum mechanics. So this is your covariant perturbation theory in field theory, quantum field theory, and in particular for the QED theory. So here, this is the, for now, this is a general expression which you could use for anything, even for gravity theory, if you want to construct as matrix for the gravity theory. However, here the simplest example that one could take would be the vertex of a QED theory, or the interaction Hamiltonian for the QED theory. So this is psi bar into A slash into this. A slash is your A slash is gamma mu, and this is at the point x. So this is for at the point x, and about this is the normal ordered product. Normal ordered product of, let me take, so there are two conventions. One is you put the quantity inside this bracket, whether square or little or whatever kind of bracket. So normal ordered product of these two things. And if you write double dot here, and I'm sorry, double dot is missing here. So if you put double dot here, and anything between that, so that is a normal ordered object. And what is a normal ordered object for a dagger? By definition, is plus minus a dagger A. So plus is for the bosonic fields and minus for the Fermi fields. So supposing I have phi of x equal to some So this is the Fock space decomposition for a scalar field. You can similarly write down the Fock space decomposition for the scalar field psi, and for the vector field A mu. Here it's only, this is the annihilation operator, this is the creation operator, and this is the plane wave expansion. So this is a Fourier series expansion of a scalar field. And if you write it for the Dirac field, then you would have some this thing, and you would have something like this, and e to the power something like this, and let me call it d dagger, C d dagger of P and V P e to the power I x by x plus. Okay, and so here these are fermionic in nature, the annihilation operator and the cation operator, and these are the spinors because psi is a spinor. If I were to write it for psi of x, then this would be a spinor, and this would also be a spinor. One of them is a positive energy spinor, one of them is a negative energy spinor, and so on. And similarly, if I write it for a mu x, then I would have some annihilation and creation operator. Let me just write them. A of k, they would be bosonic, and here I would have, if I write it for a mu, epsilon mu r, and times e to the power minus itx, and either a dagger of k. If it is real, then I would have, otherwise I would have a star or dagger, depends. So usually they are taken as real. So these are polarization vectors. In the case of the vector field, you have polarization vectors here. In the case of spinor fields, you have spinors here. And here, for the scalar field, you do not need to introduce either of u and v or the polarization vectors. So the main point is, this is just to give you an idea and of what is going on here. Now I again come back to the and this object T here is the T here is the time ordered product. So time ordered product of, let me write first for the phi of x, phi of x prime, then this is theta of t minus t prime into phi of x into phi of x prime plus theta of t prime minus t into phi of x prime into phi of x. So the product of phi and phi, and for, okay, so this is for the product of the scalar field. So here this object is defined as theta of t minus t prime is 1 or 0 if your t is greater than t prime, if t prime is greater than t, okay, or t minus, okay, this is the same thing, t minus is greater than 0, or, so it's okay, all right. And but for the spinor field, t of psi of x, psi of x prime, this is theta of t minus t prime, psi of x, psi of x prime minus theta of t prime minus t, psi var of x prime, psi of x. So this is equal to psi of x, psi bar of x prime. This is psi bar, psi bar, psi bar, psi. Okay. So this, if t is greater than t prime, and minus psi bar x prime, psi of x, t prime is greater than t. So because the spinors, they are fermionic objects, therefore they are anti-commuting. So if you flip their positions, you pick up a minus sign. That's the only point. Okay. So coming back to the so we have defined everything. We have defined our time ordered product and normal ordering. Let me explain a little bit further. Let me leave this term here. So because we want to understand this little bit further. So normal order product of phi of x and phi of let me have phi of x at the same point. So what you have is phi, when I expanded when I wrote down the Fock space decomposition, the first term actually is phi plus of x. Let me write it again. Phi of x, then you make a Fock space decomposition. So this is phi plus x plus phi minus x. So the first part, which involves your a and e to the power minus I kx, this part corresponds to the positive frequency part. So positive frequency part corresponds to the annihilation operator, and this part corresponds to a dagger of this part corresponds to the creation operator. So as I said that my product of a dagger and normal order product. So if depending upon the bosonic or fermionic, so a daggers have to stay to the left and a